Let's now move on to today's main subject, and it's a lecture on the birth, life, and death of stars. It's really a great pleasure for me to introduce today's speaker. Today's speaker is James Kaler, Professor of Astronomy at the University of Illinois. Jim earned his undergraduate degree from another Big Ten school, Michigan, and he got his doctorate from UCLA in California. His research area is to do with stars that are undergoing a dying process, and he's published over 100 papers in that area. He's also received a number of, many delightful honors, including 2 medals. In addition to his numerous research activities, Jim has made an enormous and highly successful effort to bring astronomy to a wider audience through articles in magazines, through public lectures, and also through his several splendid books.
I also have to find the light switches. We went over this. Let's try. I'm going to try this and see how it works. If it doesn't, I will turn them back down again. Sunset. You don't pay much attention to the sun in the sky most of the time. Most of the time in Illinois, you can't see it anyway, so it doesn't make much difference. What is it? Where did it come from? Where is it going to go? People live relatively short lives. They think it's going to stay there forever. And you usually see a wave of depression move through an audience when you tell them in 5 billion years it's going to die. And the feeling is, well, then do I really have to do my homework and hand it in if the sun is going to die anyway? But 5 billion years is a very long period of time, and over a human lifetime it doesn't change much. But yes, it will die, and yes, it was born somewhere around 5 billion years ago. And it's not alone out there in space. There's lots of others. This is a field of view maybe 5 degrees across or so in the constellation Sagittarius, which is slipping away to the west, in the middle of the Milky Way, which very few people get to see anymore because of all the bright lights in the area from where you live. But if you are to go out 20 miles into the countryside, you would see a band of light across the sky, the disk of our galaxy, and with the naked eye you see the combined light of maybe 100, 200 million stars. There are an awful lot of them out there, and in the galaxy in which we live there are about 200 billion of them. And they had to come from someplace, and they're going to have to go somewhere else. They have to be born, live very different lives in some cases, and then they're going to have to die. Back 3,000 years ago, the world was said to be born or through the battles of the gods. Kronos, who's now known as Saturn, fathered Zeus or Jupiter. And to control the world, they had an epic battle, one of the greatest battles of all time. Zeus won. And as a result, the gods, not the Titans, control the world. We're going to look at a battle of the Titans and the gods today, but not in the form of anthropomorphic gods, but in the form of the forces of nature, because that's really what this is all about. Now, I was awed to stand here and watch these wonderful demonstrations, and I guess what I should do is take a cue from you and ask for a volunteer from the audience. We're going to do a remarkable demonstration. Oh, come on. It won't hurt anybody and you won't get messy. You look like a good candidate because you're right on the end of the aisle and you don't have to walk over. Now, this is a dangerous one, a little bit dangerous, so you have to be careful. I have here a test particle. It's a rock. Now, hold it up in the air, but hold it away from yourself. Now, I want to show you something remarkable that you rarely think about. Notice, there is nothing between the rock and the floor. Now, let the rock go. Thank you. Excellent. It falls. Isaac Newton, again, falls under the force of gravity. Newton, of course, did not discover gravity. No physicist discovered gravity. Gravity was discovered by the first caveman to walk off a cliff. Ah, gravity. Down he went. Newton found out how it worked, at least a pretty good approximation to how it worked. It's one of the 4 forces of nature, and surprisingly enough, it's the weakest of them all on an atom-to-atom basis. The forces of nature in this case being the ones that act over a distance. And what star formation and stellar evolution and star death and star lives are all about is the interaction among the various forces of nature, each one trying to gain ascendancy over the other, particularly 2 of them, gravity. And nobody knows why there's gravity And I can ask a physicist, as an astronomer, I don't know, and he doesn't know either, and no physicist knows. You can describe it beautifully, exquisitely, how it works, but nobody knows what causes it. Now, the next experiment, that's the weakest of them all. Now, you look at the strongest of them all. I have here a small nuclear device which involves the strong force. And when I push the trigger on the nuclear device, Champaign-Urbana will disappear, and there will be a hole in the ground. It's the strongest of all forces. Maybe it'd be best to show a picture instead. Devastating. The strong force is the force that holds the atomic nuclei together and keeps atoms from flying apart. An enormous amount of energy involved, and when you release that, you can obliterate islands. You can obliterate almost anything you like. And it's really the battle between gravity and the strong force that makes for stellar evolution, star lives, and star deaths. And there are others. The strong force has an ally in the electromagnetic force, which also tries to counter gravity. But gravity, like Zeus, ultimately wins the battle, as you'll see. And watch the interplay of forces as we move along. There's a fourth one rather. Gravity is the weakest, the electromagnetic force in between, and then the strong force, aptly named on top. And the curious thing is it's the weakest of them all, which is finally, ultimately, the victor. And the one in the middle, which is called the weak force, we'll introduce as we go. You see this in the winter sky. January, you look out in the evenings, you see the great hunter standing up there, the bright star Betelgeuse, Rigel down here, Orion's belt. Some of you may be familiar with it. A bright, beautiful constellation figure. Orion's sword hanging down from the belt, and right in the middle, a kind of a fuzzy thing, which you can see with binoculars, and when you look at it up close, you see the beautiful Orion Nebula. A large cloud of interstellar gas, and what most people who look into the sky don't realize is that a vast amount of matter lies in the spaces between the stars, the interstellar medium, and it comes in a huge variety of forms. In these huge clouds of gas, which contain hundreds times the masses of the sun, you take a look at the close-up of this, and in the middle, and this is a Hubble Space Telescope mosaic of the central regions of the Orion Nebula. It's a little quartet of stars in here. The brightest of them right here is producing so much ultraviolet radiation that it causes the surrounding gas, which is a few light years across, to fluoresce and radiate back at the Earth. These things are highly structured. There are all kinds of physics going on here. There's a huge shock wave. You can see the delicate filaments of literally sonic booms. These things carry sound waves throughout them. And huge splotches, areas here where there doesn't seem to be much gas. And in fact, much of the structure you see here, and much of the structure that you would see in the Milky Way, is the result of interstellar dust. Clouds of thick dust that lie in the spaces between the stars, in between you, the observer, and the background. And you can see this dust all over the place. This star up here is the left-hand star of Orion's belt, and hanging down from it is this beautiful ribbon of red light. The red light is coming from hydrogen radiation. Hydrogen is the dominant element in the universe. About 90% or so of all the stuff in the of all the atoms in the universe are hydrogen. Around 10% helium, and the little residual is everything else. And with that as an aside, you begin to see the uniqueness and the beauty of the Earth because it is the distillate and it is the everything else. We hardly have any hydrogen and helium here at all. Little blob of material sort of working its way into the bright stuff. If you put your head over on the right, it looks like a horse's head, and astronomers, being the brilliant people that they are, have ever called this the Horsehead Nebula. You find over on the left-hand side a lack of stars, not very many of them. Over on the right, there's whole bunches of them. This whole area here is filled with dark dust and a huge intrusion of dust going into the bright stuff. In fact, you can see a bright rim around it here. These are involved with each other. There's a shock wave as the dark stuff penetrates into the light stuff. There's all kinds of interactions going on in here, and in part it's the interactions that will ultimately cause the birth of the stars. all kinds of other nebulae. Fix your eye on this one because I'm going to show you in a little while an infrared picture of this. The dust is almost impenetrable in the optical part of the spectrum. It's trying to look several miles through a thick fog. You simply can't do it. But you don't have any trouble listening to a radio station through the fog. The long waves of radio waves penetrate the fog very nicely, as would infrared radiation. And when we were able to get infrared telescopes, we could look into these thick clouds of dust and watch our stars being formed right before our eyes. So keep your eye on this one. You're going to see a similar image, but in the infrared in a little while. The dust clouds are everywhere. They look like holes in space, but you can see bright rims around them where the dark stuff hammers into the light stuff, or the light stuff is trying to push into the dark stuff. The stars you see here lie in the foreground, between the cloud of dust and the background. You can't see anything through this thing at all. You know, there must be somewhere around 1 grain every cubic centimeter or so. Not very much. And it's not like the dust you'd find on your living room, your dining room table. The dust grains are only about 1,000th of a millimeter across. It's testimony to the enormous path lengths through which you must look that shows the darkness that blocks the light. You're looking through a light year, perhaps, and the effect of the dust simply accumulates and blocks the light of the background almost completely. The dust grains, which are not quite this large, they say they're about a 1,000th of a millimeter across, we found spectroscopically when you take the light from the stars and spread it out into a spectrum, into its component wavelengths, you find that the dust grains, where in the cases where you can see some stars through some of the clouds, the dust grains superimpose the absorptions that are caused by carbon. They're superimposed by silicate, and they're mostly carbon or silicate grains on which there have been laid down ices in which there are all kinds of metal atoms embedded in. It's a very complex structure. We've actually found these things embedded in meteorites. And we begin to see where our own sun, of course, and our own planet have come from. The dark dust clouds hide the interiors from the light of hot stars. Interstellar space is flooded with high-energy radiation from the background stars. But if you get into a dust cloud, the temperature of the gas is going to go way, way down because none of the light can penetrate inward. In the heart of one of these clouds, like the one I showed you before, the temperature might plummet to only a few tens of degrees above absolute Kelvin, above absolute zero. It really chills down in the middle of these things. And this promotes a wonderful and sometimes bizarre chemistry. When I was back at the University of Michigan, as we used to say, I was told, you don't need to learn anything about chemistry. Astronomers don't need to know chemistry. There's no molecules anywhere. I mean, the stars are too hot for molecules, and there's nothing much in interstellar space anyway except a few little radicals, so who cares? Until we were able to penetrate the dark dust clouds with radio telescopes, or rather look at the radiation in the radio coming out of the dark clouds and the low energy spectrum lines and be able to detect molecules in interstellar space, beginning with such things as simple radical OH and progressing through to water, various alcohols. You see a molecular structure of ethyl alcohol up here, and then a curious variety of long-chain carbon molecules of the kind you cannot produce on Earth. They're much too fragile, but in the low temperature, low density conditions of interstellar space, you can make them. Benzene ring down here, we don't find benzene, but we find them stacked together, linked together into polycyclic aromatic hydrocarbons. They're stinky molecules, why they're named that. Very complex groups of benzene molecules linked together. C60, Buckminster fullerene, buckyballs, they're sometimes called. There are now 109 known molecules in interstellar space, including the only spectrum I'm going to show you, what is a tentative discovery of the amino acid glycine. We're looking for biomolecules now in interstellar space. Glycine is, and the amino acids are the foundations for proteins. Proteins are the foundation for life. And then you begin to wonder, did life itself, or at least the seeds of life, begin to arise in interstellar space? I think the next 10 or 20 years is going to show some remarkable progress in the field of molecular astronomy. Well, now we'll look back at that cloud that I showed you up near the left-hand star of Orion's belt, and you look into it with infrared radiation. Rather, you look at the infrared radiation coming out of it, and what do you see in the middle? but hundreds and hundreds of stars. And you couldn't see anything in that cloud at all. There was a big black cloud running right through it. And in the middle of the cloud, we're finding brand new stars. We find these things everywhere. One of the most famous pictures that now ever taken, I was on the cover of Newsweek, probably several other magazines, in a gaseous cloud called the Eagle Nebula M16 in the summer sky. The Hubble Space Telescope zeroed in on 3 long, well, they're called elephant trunks in astronomy for obvious reasons. And with the enormously high resolution of the space telescope, you can see little blips up here at the top. There's a very bright star up where the laser pointer is here, very hot one. And it is gradually melting away, evaporating away the tips of these columns. And it's revealing stars that have been born in the centers. You can begin just to see them coming out of their cocoons up here. There's no doubt whatsoever that stars are born in the hearts of these dark clouds. We're finally finding where they come from. How are they born? It's a brand new star right here. How do we know it's new? It has some curious characteristics. It's anomalously bright, enormously bright in the infrared. It's radiating a lot of infrared radiation, much more than the sun would. And we surmise that that's because there's this cloud of dust surrounding it, and the dust is re-radiating light from the star. It's enormously bright in the ultraviolet, high-energy radiation, much more than our ordinary sun is. And we're surmising that that's because this star, this brand new star, is actually accreting matter and growing from interstellar space. And as the mass falls down on it, it heats the star and produces high-energy radiation in the ultraviolet. Well, it used to be thought, and in fact, the concept that stars come from interstellar clouds has long been surmised. It used to be thought that, well, you just get a self-gravitating blob. Think of me as a self-gravitating blob. And I get smaller and smaller under the force of gravity. I get hotter and hotter in the center until I turn into a star, and it's a nice, gentle operation like that. It doesn't seem to work that way, something that the theoreticians never guessed at all, and I don't think ever would have guessed. Theory is driven, is it not, is driven by experiment. I think it's fair to say, okay, we don't make theory from whole cloth. We have to have the observations. And then the theorists, when you present them with new observations, scratch their heads and say, well, I guess we got that wrong. We'll go back and develop or improve the theory to fit the observations. Nobody ever figured out what brand new star. The theoreticians never guessed, never could have guessed what brand new stars are going to do. Back in the 1950s, 2 astronomers, Herbig Haro and Guillermo Haro from Mexico, independently found funny-looking blobs out here in interstellar space. They thought for a time that these were actually new stars contracting under gravity. And there they hung for a long time. They were curious objects. They were referred to as Herbig-Haro objects. And then in the 70s, we found that they came in pairs. There was one here and one here, and often one of these brand new stars in the middle. Another reason we know it's a brand new star, by the way, is that it has very powerful absorptions of the element lithium in it. Lithium is a fragile element. It's destroyed by nuclear reactions very easily at low temperatures. The surfaces of stars are under a state of convection, the gas flowing down and then back up again. And in the surface of a star, it would take its natural lithium and bring it down to the temperatures where it's destroyed. The sun has very little lithium in it at all. These brand new stars here have a lot of them, so lithium becomes a key for looking for new stars. Coming out of the star is a jet. And you can see vividly what's happening here. The jet is sweeping up in a series of shock waves, sweeps up interstellar matter and rams into it here. And you literally have an enormous sonic boom somewhere around a light year away from the star. This gas is streaming out at several hundred kilometers per second. Now, there's another Herbig-Haro object here, no jet, but the thing is tilted. There's all kinds of dust. This one's coming at you. It's in front of the dust. The other jet must be hidden behind the dust in the background. But it is surely there because there's the Herbig-Haro object up there. Now, the star is not gaining mass, it's losing mass. Brand new stars get mass and lose mass at the same time. An absolute surprise. And when we look into the dark clouds themselves, we see even newer versions, protostars, stars that haven't even really begun to form. or have only begun to form, blowing out matter. This is an image made in a spectrum line of carbon monoxide in a specific emission at a specific radio wavelength. And one of them is coming at you. The light is Doppler shifted to the blue. Some of it is going away from you, and it shows a jet streaming out of the center. Ammonia radiation, ammonia spectrum lines, emissions in the radio spectrum come from high-density gas. If you were to look at this in the light of, or in the radio radiation of the ammonia molecule, you would see a disk perpendicular to the flows. That is, the jets are coming out of a disk. The disk is somehow focusing the jets. From that, we put together a picture of how stars begin to form. And one of the most remarkable things is that it takes the whole galaxy to produce it. There's a rubric, in fact, Hillary Clinton wrote the book, It Takes a Village to Raise a Child. It's an old African saying. And in fact, it takes a village to raise a star, the village being the galaxy as a whole, and the galaxy as a whole creates the stars within. This is a painting. It's called A Portrait of a Galaxy, and it's our galaxy of 200 billion stars, and it's an attempt to put things in proper perspective, where they belong, real astronomical objects. And our sun is somewhere around in here. I couldn't possibly point it out because it would only be a little tiny blip. It's a minor star in a major galaxy. The other ones here are stars that are either very massive, the bright ones you see, or stars in the act of dying. But ours is about here in one of the spiral arms set off to the side. If you take an ionizing gas, an ionized electrically charged gas, and you move it, you will generate a magnetic field. The sun spins. The outer parts are in a state of convection, churning gases. The sun is rotating. The gases then churn around. The ionized gases generate the sun's magnetic field. The Earth's magnetic field is generated by convection in the Earth's liquid outer core in combination with the Earth's rotation, which produces Coriolis forces and causes a complex rotational pattern in the center of the Earth. The galaxy does the same thing. It's rotating. Many of the gases are ionized. You saw, after all, the Orion Nebula. And in the spaces between all of these nebulae, there are also low-density ionized gases everywhere. If you spin the galaxy around, and why does it spin? Well, if it didn't spin, of course, it would all fall into a lump in the center, and none of us could exist at all. Everything out there has got to be rotating for its very existence. The rotation of the galaxy generates a magnetic field. It's weak. It's about 1/1,000,000th the magnetic field strength of the Earth. But taken over the vastness of the galaxy, 100,000 light years across, it is an enormous amount of energy. Somewhere around 1/3 of the energy of the galaxy is tied up in its magnetic field. The magnetic field threads its way through the clouds of interstellar dust. And we put together a picture something like this of how stars are formed. The magnetic field, it takes it all to do it. That's the remarkable thing. The magnetic field threads its way through the clouds of interstellar dust and gas. If through accidental processes, accident is a part of nature after all, through accidental processes or compression by a nearby exploding star, compression by a powerful wind from a nearby hot star, perhaps other means, you can get a cloud of the gas dense enough so that it begins the contraction under the force of gravity. If it's not dense enough, it won't. It'll probably dissipate away. So you have to have a compressional means. The gas will be slightly ionized. Even if it's cold in the core, cosmic rays can ionize the gas. Cosmic rays are high-energy particles produced, we believe, in exploding stars. They can penetrate anything. The most energetic cosmic ray ever detected. Cosmic rays are atomic nuclei. That's all they are, little particles. They run up through, I think, the heaviest one, bismuth. Most of them are simply protons. The most energetic cosmic ray particle ever detected has the energy of a professionally pitched baseball, one nucleus. And consequently, they don't get stopped by the clouds of interstellar dust. They penetrate through and they partially ionize the gas within the cloud. That allows the magnetic field to grab on to the collapsing cloud. I am a cloud out in interstellar space. This is beginning to sound like some kind of 60s thing, isn't it? Of a cloud in interstellar space. I'm rotating. Everything is going to be rotating. Now, under the relentless force of gravity, I begin to contract. And they contract, they spin faster and faster. And as you spin faster and faster, of course, your arms fly out, you flatten out, and then you fly apart and you splatter all over the wall. And consequently, stars can't form because of the conservation of angular momentum. And we wonder how we got here in the first place. Well, the problem that the star faces, astronomers love anthropomorphism. We really think stars are alive. The problem that the star faces is that it's got to get rid of that angular momentum somehow. Otherwise, none of us could possibly exist. And stars have figured out how to do it. Or somebody has figured out how to do it for the stars. And in part, it's the magnetic field. The magnetic field is generated by the entire galaxy. It grabs onto the collapsing blob, which is trying to push downward. That squeezes the magnetic field lines together. That provides an outward force that keeps the thing from contracting very fast. So it contracts very slowly over only tens of millions of years. Well, these field lines are like ropes that grab onto it. And as a result, they break, very slowly break the collapsing cloud and provide the first way of getting rid of angular momentum. So now the cloud begins to collapse from the inside out. A star begins to form in the middle. The magnetic field lines gradually diffuse outward. It's already stopped a lot of the rotation. And of course, what happens as the star contracts, it will spin out into a disk, very much like the way, as I pointed out, is if I rotate, my arms come out by my side like this, and I spin into a disk, you see. And I flatten out. That's what's happening here. Well, there's still a magnetic field locked into it. It may be the magnetic field, a residual magnetic field collapsed down from the outside, or it may be a dynamo produced by the rotation of the disk. The magnetic field gets wrapped up, we think, and here, of course, we sound like we really know what we're doing, and we really don't. The theory is extremely difficult, but that spins some of the disk out, and that throws matter out in the direction perpendicular to the disk, which gets rid of more angular momentum. Collapsing stars have to get rid of angular momentum, and in part they do it by getting rid of some of the mass that falls onto them. It's just that the accretion rate exceeds the mass loss rate, so the star gradually grows in the middle, and we get these jets coming out of the stars. The jet slams into the interstellar medium and produces the Herbig-Haro object. There's an infrared source buried in here in the southern hemisphere. This is a Hubble Space Telescope picture. This wonderful jet with all the knots flowing out of it, slamming into the interstellar medium several light years away, building up to produce the Herbig-Haro object and the shock wave. And this actually winds up entraining all kinds of molecular gas, and you get a huge flow of matter flowing away from the star, which was ultimately slowing this star, which is buried here in the dust, down. Hubble Space Telescope picture of yet another one shows the jet pouring out of a disk right here. The dark disk, the outer part of the disk illuminated by reflection from the star buried within. You can see the disk itself and the gas flowing out of it. You look into the Orion Nebula, you see these disks all over the place. The background is the nebula, the dark one, light one. You can see some of the stars in the middle. It doesn't take much imagination to go back to our own solar system, as Immanuel Kant did in the 1700s. Look at the solar system, see that our planetary system is in the shape of a disk. All the planets going around the sun in the same direction, all in the same orbital plane within a few degrees. We've known for 100, 200 years that our solar system had to develop out of a spinning disk, and there you are. We're looking at the disks surrounding other stars, and this must have been what happened to the sun some 5 billion years ago. Through radioactive dating of our own rocks, we know that the sun, the earth, the whole solar system is a common age about 5 billion years old. You're looking at the birth of what may be a planetary system like our own. Disks, reflection of light from the center. Now, in the middle, there's a star beginning to develop. Eventually, the star will turn on. It will dissipate the dust of the disk, and we will, maybe with our Hubble Space Telescope, begin to see the planets around other stars before too terribly long. The star is contracting under the force of gravity. The whole concept of stellar evolution, stellar birth, stellar life, stellar death, involves either the various acts of contraction itself, which does some interesting things, or the pauses, the things that prevent the contraction. Ultimately, it will reach a temperature at which the protons will begin to react with each other in the nuclear sense. Protons don't like to stick together, after all. They're being forced apart by the electromagnetic force. They're both got positive charges. However, the nuclear force acts over an extremely short range of about the radius of the nucleus itself. And if you can, through some means, get those protons close enough together, now I've got two protons. I'm pushing them, pushing them, pushing them. The electrostatic force is trying to push them apart. If I can get them within 10 to the minus 13 centimeters, suddenly the strong force becomes stronger than the repulsive electromagnetic force, and they stick. Now, to do that, you can't just take protons in the lab and push them together. You don't have enough force. You've got to drive them together at very high speeds. That requires very high temperatures. It requires a temperature of the order of 10 million degrees Kelvin or greater. But in the core of a forming star, you can get temperatures like that, and then you can drive them together hard enough so that the two protons will stick together to form a deuterium nucleus. One of the protons will eject antimatter in the form of a positron, a positive electron. That involves the final force, the weak force, and that drives a positron away. But antimatter, as you know, you can't go over to chemical stores and say, give me a jug of antimatter, please, because what would you keep it in? Antimatter and matter annihilate each other when they touch. The positron will fly about that far before it hits a free electron. They annihilate each other and produce two gamma rays in the electromagnetic spectrum. The gamma rays ultimately work their way out of the sun, degrading as they go toward, as a result of reabsorption, reemission, reabsorption, reemission at lower temperatures until they escape the surface of the sun in a spray of yellow light. So we wind up with a deuterium nucleus. The deuterium hits another proton, turns into light helium, helium-3 with the ejection of a gamma ray. Two helium nuclei hit together, produce an ordinary helium nucleus, eject two protons back into the gas, and we have taken 4 atoms of hydrogen, turned them into 1 atom of helium with a loss of mass. It's long been known that a helium nucleus is 0.7% lighter than 4 hydrogen nuclei that make up the helium nucleus. That 0.7% goes into energy via Einstein's E equals mc squared. The m is the lost mass, c is the speed of light. It's a really, really big number. You square it, you get an even bigger number, and you have an enormous amount of energy from a tiny amount of mass. And that's what runs the sun. Now, the temperature of the sun is a result of contraction. The pressure inside the sun as a result of the high temperature is trying to push the sun outward. And the solar radius is a balance between the inward pull of gravity, the outward pressure of the gases. If there were no nuclear reactions, the sun's energy would come from the gravitational squeeze. And the sun could live for 10 million years. And as long as there's any hydrogen in the center of the sun turning into helium, the sun will stay a pretty stable body, won't change very much. And we calculate theoretically that it should take the sun about 10 billion years to convert its hydrogen into helium. It doesn't blow up because this reaction is a very slow one. On the average, it takes 5 billion years for a given proton to hit another proton with high enough energy to turn into deuterium. And this slows the whole reaction. Once this happens in 7 seconds. So it's this, then bang, bang, you've effectively got your helium. So the sun does not become a hydrogen bomb. It's a very beautifully slow, wonderful nuclear reactor. All of this action has to take place down in the center, down in the core of the sun. The inner 40% or so of the mass, only about 5% of the volume of the sun, inner quarter or so of the radius. The density in the core of the sun is approximately 160 grams per cubic centimeter. And it's a beautiful, beautiful, stable nuclear reactor. The pressure of a gas depends upon the number of atoms, not what they are, not the kind. So you're taking 4 particles and you're converting them into 1. You're reducing the number of particles. And that results in a contraction of the core. The contraction of the core keeps it stable. So as you reduce the number you reduce your fuel supply, the amount of hydrogen, the temperature goes up a little bit as a result of contraction, which increases the rate of the reaction, and one offsets the other, and the sun sits there almost stably for 10 billion years. We're about halfway through, 5 billion years left to go. Keep your eye out for what's going to happen. The sun actually, a graph. This is a theoretician's version of what is called the Hertzsprung-Russell diagram. If you take an astronomy course, you will look at the empirical version, which is what ultimately drove the theoretical version. Astronomy being what it is, we plot temperature from right to left, increasing rather than from left to right. Everything has to be done backwards in astronomy. Fortunately, the luminosity in solar luminosities is climbing upward, not downward. We at least were able to do that much. We find that stars lie along what we call a main sequence, and I'll show you that in a little while. Show you the whole thing in a little while. Low mass stars down here, this goes all the way down to the floor, all the way up to the ceiling. High mass stars up here, the main sequence being a mass sequence. The greater the mass of the star, the greater its luminosity. It's burning in the nuclear sense, burning its hydrogen in the core. Now, it's not a perfectly stable reactor. When the sun was born, when the nuclear engine turned on and the star stabilized with its spinning disk, the planets forming in the disk, it was about 70% less bright than it is now, notably dimmer, we think, than it is now. What kept us all alive back then, we really don't know. It's a mystery. We're sitting right here now, and about 1.5 billion years we'll be up here, another couple of billion up here. At about this point here, the sun will be hot enough probably to boil the oceans away. We may turn into a Venus-like body. We won't survive, really, the hydrogen-burning lifetime of the sun. The Earth will, but life probably will not. And after about 5 billion years, ultimately, the core hydrogen has to run out. And that's when the fun starts for somebody else, as long as it happens to somebody else. At that point, the nuclear reactions can't keep the core up anymore, and the core must collapse. Well, collapse astronomically means it's going to take 1 billion years or so, but it will contract much more rapidly. And the sun will begin to heat at the core, the outer layers will balloon outward, and the sun will cool at the surface. The core contracts. You're looking at a star with a contracting core. Most of the mass will contract down to this, and then down to this thing in the middle with a little tiny helium core, and the outer part of the star will balloon outward to become what is called a red giant star. The working part of the star is contracting under the force of gravity to almost the size of the Earth, with a density of close to 1 million grams per cubic centimeter. That in proper SI units is 17 1957 Cadillacs per golf ball. So it becomes an enormously high density. All of that energy, what happens is that you're using an enormous amount of gravitational energy all of a sudden. You're not holding the gravity back anymore. The nuclear fire goes out, huge amounts of energy get released gravitationally, and that drives the outer part of the sun or the star outward. And the star climbs up the diagram here, higher and higher, becoming 1,000 times more luminous than it is today. That is not going to do the Earth any good. The outer parts of the star will expand. They will reach the orbit of the planet Mercury and vaporize it. Mercury is doomed in about 6 billion years. It doesn't know it yet, but it's going to find out. The outer part of the sun will expand. This is a view of an Illinois cornfield 5 billion years from now, with the sun rising over the horizon about the size of the constellation Orion itself, about 10 degrees across, taking over an hour to vault the horizon. Well, let's make it an Iowa cornfield. At some point, the ash of the old reaction, the helium, will become hot enough to fuse into carbon. It's called the triple alpha process. Helium nuclei are also called alpha particles. 2 of them bang together to form a beryllium-8 atom. Well, you can't buy beryllium-8 either. Its half-life is around 10 to the minus 15th seconds. So as soon as you make it, it falls apart. But if in its fleeting existence, you can whack it with another helium nucleus, that is, bring 3 helium nuclei together, you make carbon. And that stabilizes the star again for a short period of time. The nuclear reactions turn on. The strong force says, hey, wait a minute, I'm not done yet. That holds gravity at bay for another, in the case of the sun, billion years, and the sun will then go back down here, and it will sit here as a very bright body, 100 times brighter than it is now, fusing its helium kind of happily for a while. Of course, it's killed off a lot of the inner planets at this point, but the outer planets are going to enjoy it, a sun that warm. But eventually, the helium is going to run out as well. It's not an infinite supply. And then the core starts its relentless contraction once again. The star climbs back up again, becoming almost 10,000 times brighter than it is now. The sun, at least, will have that behavior. Here's the main sequence again. 5 solar masses will have a somewhat different track. We are making elements. We're making heavy elements out of light elements. We're taking hydrogen, making helium, taking the helium, making carbon, and in fact, even oxygen out of it. We now have a contracting carbon and oxygen core. It's surrounded by a shell, which is still fusing some helium. The strong force doesn't give up easily like Kronos did. It hangs on as long as it can. Helium, hydrogen reactions going on out here. The core contracting ever further. The star becomes even bigger than it did before. The sun will reach the orbit of Venus. It will reach the orbit of the Earth. It may even approach the orbit of Mars. This is sunrise on Mars in 6 billion years. The sun vaulting the horizon of Mars like this, if it doesn't vaporize the planet entirely. All kinds of wonderful nuclear reactions are beginning to take place in the core. Here is an example. This is called technically it's called the S process for slow neutron capture. We're starting here in this example with yttrium. Captures neutrons, turns into higher isotopes, hits one that's radioactive, it jumps to zirconium. The zirconium picks up neutrons until it becomes radioactive, drops back to niobium, keeps picking them up, and we build up the periodic table inside the star. How do we know that? Element technetium, number 43, does not exist on Earth. There are no stable isotopes. Yet we see technetium absorption lines in the spectra of these stars. The stuff is being made before our eyes. It's a chemical factory, alchemy in front of us. The star loses mass. Hey, you got a star as big as the orbit of the Earth. The surface gravity is so low you could probably, if you could stand on it, you could spit off it and put the spit into orbit. I'm sorry. But the enormous luminosity of the star at 1,000 solar luminosities, coupled with the low surface gravity, means that you're just going to evaporate the surface of the star away with a physics that is not very well understood, I must say. Here's a blob of gas going out from a star in the middle. We know there's a star in the center. You can detect it in the infrared. This is over a light year across. And at the last gasp, the nuclear burning core is revealed, surrounded by a shell of gas that is expanding into space. You're looking, in a sense, at a transparent star. The old hydrogen envelope of the star, the inert envelope that didn't partake in nuclear reactions, is expanding outward, revealing what used to be the carbon-oxygen, is the carbon-oxygen core of the star, and we have what is called a planetary nebula. Now, thanks to William Herschel, who discovered these things, and he looked at them back in 1780-something, and he said, well, they're disk-like. I'll call them planetary nebulae, like meaning disk-like objects, to the perpetual confusion of everybody ever since. They don't have much to do with planets, except that they're providing some gas out of which planets might form someday. Otherwise, they have no relation to planets whatever. Well, they probably partook in the destruction of this star's planet. This is a lovely little object up in the northern hemisphere called the Cat's Eye Nebula. And this is a ground-based picture. You can see beautiful swirls of gas expanding away at about 20 kilometers per second. Take a look at this, just to look at the contrast as to what the Hubble Space Telescope can do. Here's a Hubble Space Telescope picture of the same thing. See the same swirls, but now you see them in exquisite detail. The star in the middle, bipolar flows coming out of it. There must be, again, some kind of disk that developed perhaps as a result of rotation, perhaps developed as a result of a double star system. We don't know. These planetary nebulae will get bigger and bigger. This is the Helix Nebula in Aquarius. It's over a light year across from one side to the other. The gas dissipating away, the old nuclear burning core right here in the center, on its way to becoming what is called a white dwarf, a star which is ultimately, the ultimate in, well, one of the ultimate stages of gravitational contraction. The gas will dissipate completely, leaving the nuclear burning core behind. The constellation Orion again, from which we started. The Orion Nebula is sitting right here. Go over here, you'll find a star called 40 Eridani in the constellation Eridanus. You look down in the star. Here's the star itself. Right next to it is a little bitty blip, a white dwarf, a star stabilized forever by its electrons, which refuse to allow the star to contract any further. As a result of quantum mechanical effects, the electrons behave something like the electrons in a metal. They're called degenerate. You can't push them together any farther, and gravity can no longer squeeze it together, and it claims a victory. At this point, the star is dead. It will cool off over the next several billion years, ultimately disappearing from view. But the most fun comes with the high-mass stars. Continue the main sequence up here. Temperature climbing to the left, luminosity here. 15 solar mass, 20, 25, 40, 60, 120 solar mass star radiating energy 1,000,000 times that of the sun. If you take a star like this and put it where, say, Vega, which is overhead in the early evening, is now, you could almost read by the light of that single star. It would be so bright. The temperatures are so high that within only a few million years, that 120 solar mass star will use all of its hydrogen fuel. Gravity begins its contraction. And we start a same sequence we had before, except these stars become enormously large. This is called a supergiant star. It is well, the one I've drawn in here is a naked eye star called Mu Cephei. You can see it in the autumn sky compared to the sun. The sun's big. These things are a lot bigger. If you plot that where the sun is, it would extend out to the orbit of the planet Saturn. It would fill the entire solar system. These things lose mass at an unbelievable rate. The Hubble Space Telescope of a southern hemisphere star known as Eta Carinae. There's a 100 solar mass star buried in here. It's losing mass with a bipolar flow. The same thing that we keep seeing over and over and over again. In the 19th century, it was thought to lose mass at the rate of 1/10 of a solar mass per year, burying itself in dust, the dust flying out back into interstellar space. All of the dust we need in interstellar space has come from evolved stars. As the gas leaves the star, it condenses into dust. Not only for these stars here, but for the lower mass stars like the sun. All these dust grains have come from evolved stars. The stars are convecting in their outer parts. They reach down inside. They dip out the byproducts of thermonuclear reactions. The carbon that we recently made gets thrown and ejected back into interstellar space. These stars like Eta Carinae are doing exactly the same thing. And then they go through a whole stage of nuclear burning. The carbon core begins to fuse to neon, magnesium, and oxygen. When the carbon's used up, the neon core contracts. That begins to fuse to silicon and sulfur. That contracts. That begins to fuse to iron. The star begins to layer itself. We're making the element iron in the center. Iron is the most tightly bound of all atomic nuclei. You cannot fuse iron and get energy out of it. As a result, the iron core collapses. The star has been alive now for somewhat of the order of, in the case of a 30 or 40 solar mass star, for maybe 10 million years. Contrast that with the 10 billion year lifetime of the sun. When we reach the iron core and nothing can hold it up anymore, gravity finally claims the ultimate victory. The iron core, once it's created, collapses within 1/3 of a second. Down it goes like this. In the collapse, the iron is destroyed and turned back into protons and electrons and neutrons. The electrons and the protons merge to become neutrons, and the entire interior of the star turns into a ball of neutrons. The collapse, in which you take 1 or 2 solar masses. Start off with something the size of the sun and collapse it to the size of Champaign-Urbana with densities of 10 to the 12th grams per cubic centimeter, produces an extraordinary shock wave. In the release of energy, with the merge of the protons and the electrons and the neutrons, you create little particles called neutrinos. The neutrinos escape the collapsing star. The sun is producing neutrinos in the proton-proton chain. If you hold your hand out like this, and even if you don't, there are somewhere around 10 million neutrinos per square centimeter per second passing through you from the sun. You don't feel them. It takes approximately a light year of lead to stop a neutrino. They just pass on through everything. The neutrinos are generated in the center. The shock wave produces a blast wave that literally tears the outer part of the star apart, and you produce what is called a supernova. The star explodes with a neutron star core at the center. And can we get somebody to help me show the video, please? And I'll show you what happens in the core. This only takes a few milliseconds, this whole thing. It's a two-dimensional computer calculation, and you're seeing the collapse of the star. It takes a light year of lead to stop neutrinos. The white line here are the neutrinos trying to get out. The gas is so incredibly dense that it stops the flow of neutrinos. A shock wave is building up here. The neutrinos sit here, and you are ultimately going to watch the neutrinos blast the shock wave out of the star and the star explode. It will happen. Just watch. It takes a while to run computer calculations of a whole third of a second where all of this is taking place. You get this enormous turbulence. The neutrinos are trying to work their way out. There it goes. And it's going to blast the outer parts of the star apart, leaving the neutron star down here in the middle. This required approximately 100 hours of computer time on a parallel processing computer. Enormously difficult calculation to make. Thank you. Could you turn that off now for me, please? And you see the star blossom in the evening sky. This is supernova 1987A, and my laser pointer just went. You see the star at lower right? This star was easily visible to the naked eye, even though 150,000 light years away. The other stars you see in the field of view here are stars within our own galaxy. This thing is far outshining any of the stars in our own galaxy. Oh, you've got one here. Thank you very much. Ah, that's much better. Thanks. I got to get another one. Right here. About one of these goes off in our own galaxy every 200 or so years on an accidental basis. We have not seen one in our own galaxy since the invention of the telescope. In the devastating explosion that blows the gas outward from the center, you can see the expanding gas here. This is a result of a supernova that took place in the year 1054. We have Chinese records of a star that brightened to approximately the brightness of the planet Venus in the evening sky. It's called the Crab Nebula. The gas is expanding outward, and in the explosion, nuclear reactions turn the outer part of the star into nickel, cobalt, iron, and all kinds of other chemical elements, in fact, generating nuclear elements all the way through plutonium, none of which exists naturally on the Earth. We believe that all of the iron in the galaxy has come from these exploding stars. And in fact, all of the chemical elements beyond hydrogen, helium, and a little bit of lithium have all come out as a result of stellar evolution and of the fight between gravity and the strong force. Ultimately, these exploding stars blast away into interstellar space. This is another remnant of an exploding star in the southern hemisphere, and you're no longer seeing the mass of the exploding star, but a gigantic shock wave extending outward. This shock wave will hit the clouds of interstellar space, compress them, and act to produce new stars. The death of a star generating the birth of yet other stars. The chemical elements that have been generated in stellar evolution, that find their way into the dust, that find their way into the gas, are thus compressed. And many of the elements, much of the hydrogen, all of the heavy stuff that's compressed to form the new star has been the result of the supernova explosions themselves. It's the ultimate in recycling. In the center, you see the neutron star. There it is right here. It's spinning Conservation of angular momentum. You take something the size of the sun that's maybe rotating slowly, you collapse it to the size of Champaign-Urbana, it's going to spin real fast. Here are two pictures in the core of the Crab Nebula, which is visible in a small telescope. Right here and right here. Here you see the star, here you don't. These images were taken 1/30th of a second apart. The star is spinning, and it's much like a lighthouse on the coast. It is beaming energy into space along a magnetic axis. The magnetism squeezed down with the collapse to 10 to the 12th times the magnetic field flux of the Earth. Energy is beamed out along the magnetic field, but it's a tilted magnetic axis, the same as we find in the Earth. The star is spinning around here. If the Earth is in the way, you'll get a blast of energy. If it's not, you won't. We are lucky enough to be in the way of the neutron star in the center of the Crab Nebula, and we then see what is called a pulsar. We will see the star turn on and off as the magnetic field axis first points toward the Earth and then points away from the Earth. We have here the case of a bizarre star that's about the size of Champaign-Urbana, about 1.5 solar masses spinning 30 times per second, slowly winding its way down over the next several million years, and you'll get a whole lecture on this subject toward about when Fred Lamb comes in here not too terribly long from now. In the center of the Crab Nebula here, we can see the star right here producing shock waves, just extraordinarily active in the middle of this. And we think this is where the cosmic rays come from that ionize the interstellar clouds that ultimately allow the stars to be formed in the middle. The cosmic rays are simply the atomic nuclei produced in the supernova blast that ride the shock waves to speeds up near the speed of light and get blown out of a supernovae. And then finally, the ultimate. You're looking at a picture of a black hole. White dwarf stars can get no more than 1.4 solar masses. If they are greater than 1.4 solar masses, relativistic effects will cause the white dwarf to collapse. The electrons can no longer hold it back, and you produce a neutron star. These neutron stars are held up forever by their degenerate neutrons, quantum mechanical effects again. But there's a limit to neutron stars, which is about 3 solar masses, maybe 2. Nobody's quite sure of what it is. Maybe Dr. Lamb will tell you a little bit better what the limit is and why perhaps we don't know exactly what it is. But if you get it beyond that limit, nothing can hold the star back anymore, and it will collapse forever. It will collapse to the point where effectively the escape velocity at the surface of the star hits the speed of light. The star then disappears from view, it becomes a black hole, and you can no longer see it, and it disappears in effect from the universe, a hole in space-time. We can detect them if they're in binary stars. If they're in double stars and close enough together, the black hole may raise tides in the large star, pull matter from the large star into it, and as it cycles in, it produces X-rays. We have found several of these X-ray stars, bright X-ray stars, scattered throughout the galaxy, indicative of black holes. So we think they're there. 3 results from stellar evolution: the white dwarf, like the sun, the high-mass stars, the neutron stars, some of them perhaps, although it's never been definitely proven, some of them perhaps turning into the ultimate, the black hole. In each case, the nuclear force, the electromagnetic force have been holding actions. Gravity finally wins the battle. All of this matter goes back into interstellar space, feeds back into the dark clouds. This is a region in Scorpio. Here's Antares down here, Rho Ophiuchi up here. This famous Rho Ophiuchi, well, famous to astronomers anyway, Rho Ophiuchi dark clouds in which star formation is going on right now. Antares itself, a wonderful candidate for a supernova sometime within the next 10 million years or so, which might send its blast waves back out into interstellar space, aiding in the formation of yet more stars. All of the material from the ordinary planetary nebulae through the supernova remnants, feeding back into the dust, feeding heavy elements back into the cosmos, until ultimately new stars are born out of all of this stuff, the new stars being made out of the leavings of the old stars, of the dead stars, the disks that form around the new stars, injecting their matter back into space to get rid of their angular momentum. Ultimately, the dust that is in the disk congeals to form the planetesimals, the asteroids, the comets, which congeal to form planets like our own, which ultimately turn into what we have today. Thank you. Thank you. Thank you.